This is the second lecture for Chapter 5, Calculus 3, and it is on the del operator. Just for review, I'd like to say that for vector functions, they will all be written with a capital boldface F, and then the components will be m, n, and p. For scalar functions, they will be written as lowercase f, not bold. This is the del operator. Its symbol is this triangle with the pointy side down. That's del. You can call it del. And it consists of three vector components: the partial with respect to x, the partial with respect to y, and the partial with respect to z. Sometimes in the past we have treated, well, something like, let me just say, du by dx as though it had a numerator and a denominator. Say we were doing substitution and u equaled x squared plus 2. Okay, then we would write du equals 2x dx, as though this derivative could be separated out as a numerator, denominator, and even rearranged. This notation came forward from the idea that the derivative was delta. That's called delta u equals 2x delta x. So a little piece of u equals 2x times a little segment of x. But then we went and used it in an integral, and so we write this du by dx, and that really isn't correct. Okay, but we do it. Here we're not going to do that at all. Let me clear the screen. We consider d by dx to be an operator. Okay, what other operators do you know? You might think of the plus as an operator. Okay, what does addition do? Here's the symbol for it. Just like d by dx is a symbol for take the derivative with respect to x. That's a symbol for it. Plus is an operator. It takes two numbers and operates on them, adds them up and produces another number. Right? D by dx operates on a function and produces the derivative. So it is considered an operator. Just like plus, minus, divide, subtraction, in a sense those are operators also. Although they're operating on numbers, this operator has to operate on functions. So we split this up, and the partial with respect to x associated with the I, partial with respect to y associated with the j, and partial with respect to z is associated with k. So you see, it's an operator that's a vector operator. Okay, remember the gradient of a scalar function. It was written del f, and that's said to be the gradient, although at that time we hadn't defined gradient, the del operator. Here's the del operator that we're talking about. F is applied to this in a remotely way that's similar to scalar multiplication. The f has to go to the x, then to the y, then to the z, and the vector remains the same. The output is a vector. So here I am saying essentially the same thing on this slide. You're taking that del operator, you're applying it to a scalar function. Remember, it's applied to functions. The result is a gradient vector. Think of scalar multiplication of a vector. Here would be the vector. Okay, I'm talking about here. Here's the vector. Trying to change color and it's not cooperating. Okay, here is the scalar. In this case, the scalar is a scalar function. Now, to carry out this operation of scalar multiplication, the 15 is multiplies the 5, it multiplies the 10, and it multiplies the 20, and the vector stays the same. The output is a vector. It's important to always get the output correct, whether it's a scalar or a vector. In this case, it is a vector. Here, the f gets operated on by this operator partial with respect to x, and you get the derivative, the partial of f with respect to x, the vector stays the same. Okay, f onto the y, f onto the k component. You see the same thing that's going on in both cases. So you can think of when the del operator is applied to a scalar function, and the result that you get out is a vector, the gradient vector. This is just an example. So we have a scalar function. Remember, scalar function in this case, this one would be mapping, looks like R3 into R1. It's a scalar function because it maps into R1. And this is a scalar function. The gradient of f, and we have del f. It's just applied to it. There's no other operator mentioned in between them. The result is a vector f, partial of f with respect to x in the I direction, partial of f with respect to y in the j direction, partial of f with respect to z in the k direction. So when you take those partials, you get 12x y cubed z to the 1/2, that's in the I direction, and also you just take those other partials for the j and the k. Now you can take the del operator and you can also apply it to a vector function. So what we did before was applying the del to a scalar. Now we're applying the del to a vector. Well, for vector operations we have two of them. We have a dot product and a cross product. So there's two ways to apply the del operator to a vector function. Dot product and cross product. Okay. When del was applied to a scalar function, it was given a name, gradient. It was a gradient of f, and it was written like that. When you apply the del operator through the dot product to a vector function, the output is called the divergence, and it's written like this. When you apply it using the cross product, the output is called the curl, and it's written this way, curl f, or rotation of f. That's more British, but you can use either one of them. So you're taking this del operator, you apply it to a scalar function. It's kind of like scalar multiplication of a vector. The output is a gradient of f. Remember, this is a vector. When I take the del operator, which is a vector operator, apply it through the dot product to a vector function, the output is the divergence of f, and dot product gives you a scalar. When you apply the del operator through the cross product, you get out the curl of f, and that is a vector, because the output of cross product is a vector. So it's good to look at this in terms of the components of the vector function f. So we're taking the divergence of f, which is del dotted with f. So here's your del operator right here. Let me change colors. This is for emphasis. Here it's dotted onto a vector function. I'm using the components m, n, p for the vector function. And when you take a dot product, the output's a scalar. But as you know how to apply a dot product, the i's go together, so you end up with a partial of m with respect to x. Then the two j components go together, so you've got partial of n with respect to y. Then you're taking the k components together, and you get the partial of p with respect to z. To save room and make it easier, you can just write m and a subscript x for the partial of m with respect to x. So it's m, mx, ny, pz. And notice that is a scalar. Divergence has physical significance. It gives a measure of how a vector field is moving away from or toward a point in the field. Remember, these vector fields these vector functions are setting up vector fields. That is a whole bunch of vectors, or vector at every point in the domain, which is some subset of R3. So here's the cross product, the curl of f. So we have del right here, and so, sorry, let me erase the board. Okay. So we have del, and now what's cross product? Cross product is written as the determinant. It is the determinant of a 3 by 3 matrix. I have seen some instances where some people have used some kind of 2 by 2 matrix to represent this. Don't do that. Write the entire 3 by 3 matrix out. It's very important. It's also important to do this when you move from this to cylindrical or spherical coordinates, which we will not do in this particular class, but it will come up later. So like any cross product, we'll have ijk up in this top row. The next row will be whatever is the first vector, and we'll just put the components here. In that case, they're operators. And in the third row, we put the components of f, the I component, which is m, the j component, which is n, and the k component, which is p. Then when we take this determinant, let's say for I, then it is the partial with respect to y applied to p, or you can write it p sub y. Going in the other direction, it's a partial of z with respect to partial of n with respect to z, n sub z, etc. for all these different terms. So you're taking derivatives as you go, and you take the determinant like you would do normally. The end result is a vector. What the curl does is it measures the tendency of fluid to like swirl in like an eddy or a little whirlpool about some particular point. You see, it's a vector. You can think of it similar to angular momentum. This is a typical visual that's given for curl. Let's consider that you have a vector field and you stick a paddle wheel in it. Here's the paddle wheel right here. It has some kind of axis, right? And then if the vector field is has a curl to it, this paddle wheel will turn either clockwise or, in this case, counterclockwise direction, and the vertical axis will be perpendicular to the plane of rotation, and its length would be is the magnitude, how fast it's spinning. So the idea is you take that paddle wheel and you would stick it into a vector field. So let's say this is a vector field, and you stick the paddle wheel in right here so that the axis is coming right out of the page, and you observe which way it would rotate. Well, looking at these arrows, it's going to be rotating in this direction. The right hand rule applies, so actually the axis would be sticking into the page. But the idea is this is the curl of the vector field. The paddle wheel was just an image to sort of explain what curl is. If the paddle wheel doesn't turn at all, then there is no curl. So let's run through an example. So here's my vector field f, and let's let it have components. M will be x, y, z, n will be y, z cubed, and p will be e to the x, y, z. Now to take the divergence is the dot product of del with f. So here's del again, the dot product, and then f afterwards. When we take the dot product, we of course end up with a scalar. I'm belaboring this point because there are many errors on this. Dot product gives a scalar. Del dot f will also give a scalar. The divergence of f is a scalar. It still has xyz components. It will change depending on the location in the field, but it is a scalar value. So I've taken the derivative with respect to x of the xyz, the derivative with respect to y of the yz cubed, and the derivative with respect to z of the e to the xyz. Right here, and that's the result. Now here's the curl. So we're going to use the same vector function, but now we're going to determine its curl. So curl is the del operator, the del operator cross the vector function. So it's going to be a 3 by 3 matrix. I, j, k go up here. The components of the del operator go in the second row, and in the third row, I'll change color here, the components of f go in the third row. Then you take this determinant, and remember the output is going to be a vector, and it is. Vector fields, vector functions, vector fields, because that's what we're talking about, not the parametric equations. I just want to mention that for review. We're talking about vector field. If this vector function has a divergence of 0, the vector field is called a solenoidal field. solenoidal field. If the curl is 0, it's said to be irrotational. And if the vector field is a fluid flow and the divergence is 0, then the fluid is said to be incompressible. So these are special names that are given to the vector fields if the divergence or the curl is 0. Need to mention that there's some properties associated with the del operator, and one is that it does not commute. Look at this. This is a good review. Let's try to, on this side, f dot, this would be f applied, del applied to f. So that would be f times, or a dot product of f and the gradient of the scalar. You see, that's a dot product. The result will be a scalar, but you see that's a dot product because those are two vectors. On this side, del dot f is a divergence of f. It's a scalar. And here's f as a scalar function. So what you have is a scalar times another scalar, which is regular arithmetic multiplication. So now you can see how different the sides are, which just impresses the point that the del operator does not commute. You can't just swap out the order of, even in a dot product, of the del operator. Now if you apply the del operator twice, you get something called the Laplacian. So it's applied twice. Remember, it's a vector function, so it's applied through a dot product, del dot del, which can be written as del squared, or with this what's called a nabla, and that's another, it's an upside down triangle, or right side up, depending on how you look at it. Anyway, that's a symbol for what's called the Laplacian. You will encounter the Laplacian in physics, especially in the wave equation. And here's what it is. It is a scalar, because it's a dot product, and it is the second derivative with respect to x plus the second derivative with respect to y plus the second derivative with respect to z. Just as with the del operator itself, you can apply this Laplacian to either a scalar or a vector function. When it's applied to a scalar function, what you're actually doing is taking the gradient first, so that would be the gradient of f, and then taking the divergence of that gradient. And here's the result, just the partial derivatives of f with respect to y, z, x, y, and z. When you apply the Laplacian to a vector function, what you really do is pull that Laplacian through onto each one of the components. Like this. Okay, so remember m, n, and p are scalar functions. They map R3 into R1. They're scalar functions. So you're applying the Laplacian, and the Laplacian is going to look very similar to what you got for a scalar function, because m is a scalar function. So m in this case is taking the place of the f. So this is a result. mxx, myy, mzz. Now n, it's going to be the same thing for n. nxx, nyy, and zz, and the same thing for p. So there's your Laplacian applied to a scalar and applied to a vector function. Now there's some identities associated with the del operator, and here are two very important ones. The curl of a gradient is 0. So the curl of the gradient, so the gradient of f, you'd write as del f, curl, let me change color here, takes forever. Here's the curl, and you apply it through, of course, cross product, and that is identically 0. So similarly, the divergence of the curl is 0. So you take the curl of f, that's right here, you see this cross product, and then of course because you have a vector you have to apply this through a dot product, not just multiplication. So here's the divergence, which is del dot, del cross f, and that also is identically 0. And I will show how that works. It's also in the homework, of course. So here was the first identity. The curl of the gradient of f is 0. So here's the gradient of f, and the gradient of f looks like this: f sub x in the I direction, f sub y in the j direction, f sub z in the k direction, remembering that the subscripts mean derivatives, partial derivatives. Now I'll take the curl, del cross. So I have ijk up here. I have in the second row are the components of the del operator. On the third row are the components from the gradient. When I work that out, now look what I get. Let's look at the I term. I get f z y minus f y z. Okay, if Clairaut's theorem applies, Clairaut's theorem states that if all the partial derivatives of a function are continuous, then the mixed partials can be taken in any order. So let's say Clairaut's theorem applies, then this could be written as f xy minus, we'll just swap these two, I'm sorry, f zy minus f zy, which of course is 0. Same with the other component. So you would have f cx minus f xz. If Clairaut's theorem holds, then I can write this as f cx minus f zx, which of course is 0. Same for the k component. So the result will be 0 in the I direction, 0 in the j direction, 0 in the k direction, remembering that curl is a vector. So the output has to be a vector. For this to be 0, each component has to be 0. Here's the other identity. The divergence of the curl is 0. So here's the divergence, and it's the divergence of the curl. So the curl of f is del cross f. So del cross f I wrote here in component form. It's borrowing the result from above. And here is the del operator right here. Now, when you work this out, remember you're going to get a scalar. So I have the partial with respect to x applied to these two terms. So that will give me p yx minus p zx. Then I take these together. I'll leave the negative sign out in the parentheses just for because I want to show the operation. I'm taking the partial with respect to y onto those two terms, so it will be pxy minus pzy, and similarly for the k component I end up with nzxz minus myz. Now I'm going to rearrange these and put the p's, the n's, and the m's together, and you can see that it is the same result as before if Clairaut's theorem holds. Okay, so right here I have, looking at the first one, pyx minus pxy. Well, if Clairaut's theorem holds, I can write this as pyx minus pyx, and that's going to be 0. So that'll take care of those two. Same with the n's, same with the m's. And so this is identically 0 if Clairaut's theorem holds. Again, for review, Clairaut's theorem states that if all the partial derivatives of a function are continuous, then the mixed partials can be taken in any order.